Okay. So this is basically my one slide thing on general relativity. You know why general relativity is needed. You needed a relativistic theory of gravitation, which Newton's laws of gravitation does not incorporate. Information can travel at infinite speed effectively. So I will not get into that part, and it was also slightly inaccurate, as we know from experiments, that it cannot, if you just assume Newton's law, if you look at the trajectory of Mercury, you cannot exactly explain, even after incorporating all the effects from the planets. So this is clearly an experimentally tested theory, but no theory is experimentally tested forever until it breaks. I mean, it is always a process. Now, as you know, in the words of Wheeler, general relativity, basically you know that from the equivalence principle, we know that it's just a 1-2 minute summary. You know from equivalence principle that motion of test particles under gravitation is independent of the mass or the constituents of the particle, which gives us the idea that maybe gravitation can be explained or described using geometry, and that is what Einstein did. And in Wheeler's word, what general relativity basically does is this, or gravitation does. So space-time, the geometry of space-time to be specific, tells matter how to move, and the matter tells space-time how to curve. Basically, the geometry is fixed by matter. So I will give you one broad example of this, a cartoon example, all with my hands, so that you know, and then I will connect to gravitational waves, that what exactly happens. So suppose you have seen this example, that you take a stretch rubber sheet, which is often like depicted as flat space-time. You put a heavy mass in that surface curves, okay, and this is like saying that matter or an energy essentially telling space-time how to curve. Now you take a small ball bearing in that curved surface and you start rolling it. The motion of that test particle will depend on that geometry. So it is like space-time telling matter how to move. Now this is easy to understand in this very simplistic picture where there is a massive body which is creating the space-time geometry, and there is a test particle which is going into it. But in practice, things can be very different, especially when we are talking about binary black hole mergers, which will come to. What happens there is that you have two massive bodies, and each will basically curve the space-time in a certain way. Now mass 1 is going to curve the space-time, which mass 2 is going to follow, but mass 2 is going to do the same to mass 1. So this curvature, this movement of mass 2 is going to change the motion of mass 1, which in turn affects the motion of mass 2. So it is almost like mass 2 is changing its own trajectory through mass 1 and vice versa. So this happens because it is a non-linear theory. This also can happen in electrodynamics, for example, which makes it very difficult to solve Einstein's equations in general, okay, and only in certain regimes with symmetries or in small perturbations we can solve Einstein's equations. And in general, if we have to solve, we have to rely on numerical relativity, but even there you cannot, it is in principle solvable with numerical relativity, but only in very specific situations numerical relativity has been successful in solving these equations. Okay, so and as you know, general relativity also predicts event horizons, that is, those are black holes, and also gravitational waves. Now the equation which describes all this is Einstein's equations, okay, where the left hand side represents geometry, okay, and probably you have by now you know that why exactly this was chosen and why there are no other alternatives, simpler alternatives. And the right hand side describes the matter energy. Basically this is the energy momentum tensor, which is the rate of flow of 4 momentum through 4 surfaces. Now, this part has already been introduced, I guess, that the metric perturbations, that h mu nu is a metric perturbations over a flat Minkowski background, even though, I mean, we will assume that wherever we are considering gravitational waves, gravity is extremely weak, but in general this need not be eta mu nu, it could have a curved background metric as well. Now when you substitute this in this equation and to the linear, consider terms to the linear order, then you get an equation of this form where this h bar mu nu is the trace reversed h mu nu, but as you will see that the gauge we will choose where the trace is already 0, so the h mu nu and h mu nu bar are essentially the same, and there you get an equation of this form. This equation is very similar to the equations we see in electrodynamics, where you get box mu is equal to 4 pi by c j mu, okay, where j mu is the 4 current, which is like rho and current density vector. So you also solve this, we can solve this equation in the same way. First, the vacuum for the vacuum solution we put this right hand side to be 0. It is very much like putting box of a mu equal to 0, or you could derive from there that box of the electric field and magnetic field equal to 0, which would give you wave solution, which means that the function, this quantity is a function of omega t minus k dot r, where r is the position vector. But if the coordinates are chosen properly and all the degrees of freedom are exhausted, if you are interested, I mean, it will be taught here, but otherwise you can look at, for example, Bernard Schutz's book to see how exactly you can put various these things. And we have also written a book where we have gone little further to show that there are different ways of showing that how you can take into account all these degrees of freedom. Finally, you are left with only 2 degrees of freedom. Okay, so if the wave is propagating along the z axis, then this general solution of h mu nu in vacuum in the weak field limit and in a flat Minkowski background can be written in this form, where all the terms which correspond to time and the z axis are all 0. Only terms which survive are the xy term. This is xx and this is yy term, and this whole thing being trace free, this is the negative of this term, and the metric being symmetric in its indices, these two, these xy terms and yx terms are the same. Okay, so effectively we have only 2 independent terms, h plus and h cross. Fine. So this represent 2 polarizations. These 2 terms, h plus and h cross, represent the amplitudes, or the not just amplitudes, the 2 plane propagating polarized waves of gravitational waves. Here, of course, it is a mixed polarization, but what you could do is to write this in terms of 2 matrices. One where all the terms are 0 except 2 diagonal terms. One is 1, another is minus 1. In another matrix where all are 0 except for this xy and yx term, where you could put 1. Okay, then you could write the whole thing, and suppose the first one you call it E plus tensor and the second one you call E cross tensor, then you could write this whole thing, maybe I can put it next time, the H plus E plus H cross E cross. So these are the 2 polarization, and these E plus and E cross would be the 2 polarization states. Now coming back to this equation, if you want to solve in general, just like we do in electrodynamics, we can use the Green's function corresponding to the box operator, and you can get a solution of this kind, where this the metric perturbations could be written in terms of the second the second time derivative of the second mass energy moment of the system. So this is like moment of inertia, but again you have to subtract out the trace and so on. Okay, so but anyway, for this lecture, what will be most interesting is that the amplitude of the gravitational waves is basically this 4 by r times g by c to the power 4 into sort of the non-spherical part of the kinetic energy. Okay, this is a broad formula. Now you can see from here already that how small h is. Okay, it is, if sources are few megaparsecs away to like what we are detecting right now, or 100 megaparsec away or a gigaparsec away, this term is already very small. Then g is 10 to the minus 7, let's say in CGS, 10 to the minus 8 in CGS units, or it's 10 to the minus 7, let's say. And c to the power 4 is like, it's also extremely small. In CGS unit, it will be like 41. This 1 by c to the power 4 would be like 42, 10 to the minus 42. So these things together is 10 to the minus 50, and this is also very small. So these things can be extremely small. Okay, this whole factor is extremely small. But so that is why until you have a very large non-spherical part of kinetic energy, you would not get a significant amount of gravitational waves. Now what is significant? Because we have not interpreted h in terms of anything else. As you will see, this h leads to a fluctuation in the separation between two freely falling masses. So that basically would mean that if you have a very small number here, the fractional change that will happen in the light travel time from one of these free masses to another free mass would change by this fraction h. So if h was 1%, which would happen probably if you are like right next to a binary black hole merger, the length, I mean if you have two pendulum which are like basically freely they can move along the axis perpendicular to the suspension, there the change will be that 1%. But what happens is that in practice what we get is 10 to the minus 21. That happens because even though this term is extremely small, this term could be very large for binary black hole mergers. There we are talking about tens of solar masses, at least few solar masses, which would be 10 to the 34. That 2 into 10 to the 33 is the mass of the sun. So few solar masses would be basically 10 to the 34. Okay, and we are talking about the basically the size and so on, which would be in kilometers and so on, and but the rate of change of second derivative of that. So what basically you get here is that there are these objects, if they move at let's say half the speed of light, okay, which is what happens just before they merge, then this term becomes extremely large, and that the number of zeros you lost here, some of those zeros are compensated by this. So as finally as the end of this in the end, this extremely small number and somewhat larger, like this is also very large number but not as large, a combination gives us 10 to the minus 21. Okay, this is typically what we get. Now obviously this can this kind of rate of change of let's say quadrupole moment, this is called the quadrupole formula, because this moment of inertia is like the quadrupole moment, it's second mass moment, happens every time. Like when I speak, I move my hands, this is creating that quadrupole moment. Only thing is that, meaning this has dipole also, but a significant part is also quadrupole. The thing is that those are not detectable. It is detectable only in such situations when the rate of change of quadrupole is extremely large. But it has to be the quadrupole change. For example, if you have extremely massive body like a black hole, which is spinning about its axis, let's say it's a Kerr black hole, you will not get any gravitational wave, unfortunately, because the quadrupole moment is not going to change. If the spin axis is aligned with the symmetry axis, okay, symmetry axis in the sense of basically the quadrupole would not change if you have an axial symmetry. But when you have a binary black hole, because there is no axial symmetry, I mean you can draw a symmetry axis, but actually it is not actually symmetric, then you will get gravitational waves. If you have a pulsar, a neutron star, which is almost perfectly symmetric, but there are some deformation it has. For example, there is a small mountain there, okay? And if the spin axis is not aligned with that, let's say the mountain is aligned with the magnetic axis, like on the Earth. You know that the Earth's spin axis is not aligned with the magnetic North Pole. Similar things happen with the pulsars. So there, you may be able to get a little bit of gravitational waves, okay, if the mound or the small hill is significant enough. If you have the ratio of that, the asymmetry is of the order of 1 part in 10 million, even then we will get detectable gravitational waves. But the expectation is that it is not even that, it may be of the order of 10 to the minus 8, which basically means that Ixx, that is the moment of inertia, minus Iyy, okay, that is basically you are looking at the, if you have this rigid body sort of situation, like where you can get the moment of inertia about 3 axes, and these are principal axes, then Ixx minus Iyy by Izz, if that is of the order of 10 to the minus 7, we will be able to, we will be very close to detection of gravitational waves. But most probably it will be like 10 to the minus 8, even though nobody knows actually what it is. Maybe after we detect, people will come up with theory saying that yeah, it has to be more large, like what has happened for binary black holes. I will come to that. Okay, I think no more discussion on this is necessary. I will come to the various other sources. I have already told you about, okay, maybe I can broadly classify the sources. So there are 2 kinds of sources, meaning 2 kinds of sources based on the length of the signal, and 2 kinds of sources based on their phase evolution, okay. So you can make a 2 cross 2, like 4 sort of matrix. So some sources, short term basically means what is short and what is long. It is based on the observation time. So if something is 1 second, then we can call it a short term burst. But if the overall the signal length is comparable to the observation time we are talking about, let's say a year or so, then you can call it a long, it's a continuous wave or a long duration signal. In the short wave, there are 2 kinds of sources, short duration sources. Some are binary black hole mergers, we will come to that in a moment, where the phase evolution can be very reasonably precisely modeled. So these are, so a certain data analysis technique called match filtering can be used there. Then there are sources which are just like a burst, like a supernova, okay, where you don't actually know the phase evolution, but you sort of, but you know that there can be an excess power in a given time, okay, so you can look for a little bit of excess power in the signal. And since this excess power could be the same in all the detectors, including their phase, we don't know the phase, but you know that the phase is the same in all the detectors. Using that, you may be able to detect those short duration signals, which are like supernova. In the long duration, there are again the same thing, that whether the source phase is modeled or not. For these spinning neutron stars, for example, you can very precisely model the phase, like for pulsars. But then there is a source called the stochastic background, which is basically a mix of all the unresolved sources in the universe. That creates an excess power, again where it will not be modeled, but since you know that this stochastic noise-like signal is the same in all the detectors, then by cross-correlating the data from the detectors, you may be able to get a detection. Fine, these are the broad class of sources. Now what are the broad properties of gravitational waves? These are transverse waves, they travel at the speed of light. That is obvious from that box operator. They have two polarization states, as I said, E plus and E cross. They interact very weakly with matter, and this is the most important property to remember. Even though this made it extremely challenging to detect gravitational waves, it took more than 100 years after the prediction to detect gravitational waves. This is extremely useful for astrophysics, because gravitational waves can travel to very dense matter without getting distorted because of this low coupling, which would mean that we may be able to see the very early moments of the universe through gravitational waves. The reason is like this. As you know that there is this cosmic microwave background. I'm sure somebody must have taught that. And you know that the cosmic microwave background comes when the universe was 3.8 lakh years old. And that is because the photons were interacting with electrons vigorously, so they could not travel straight to us. For example, like I can see you because the photons are coming straight to me almost. There could be a little bit of lensing or refraction, but if I put some smoke here, photons will still come, but they will get scattered so much that I cannot form an image. So this happens for in case of the early universe also, assuming that it has a very hot history. But because the universe was expanding, the energy was going down, electrons could get captured by the protons, they form neutral hydrogen, and the scattering or cross section of those with light went down. So the light could start basically travel straight to us after their final scattering, which is the last scattering surface. So the problem is that we cannot go beyond that because the universe was very dense before that. Then how do we get the picture of the universe when it was like less than a second old? Because, and that is extremely important, because the whole present Big Bang cosmology is based on, will be self-consistent only if we have a rapid phase of expansion when the universe was a fraction of a second old, okay? And half of the expansion of the universe, or in terms of the E-fold, that is in log scale, happened during that period. So we have to really probe that part, and gravitational waves is a very strong candidate for that, because the gravitational waves which were generated at that time can still exist right now, because they interacted very weakly with matter even after they entered the horizon and so on. Okay, now so basically these are the ways, and also, you know, if something is happening near the dense core of a galaxy, okay, let's say two black holes are merging, you would not be able to see it, but with gravitational waves can still come through, because it is basically matter is gravitational. For gravitational waves, matter is sort of like transparent medium. Yeah. So when you
were saying that the gravity wave signal of Big Bang era or something like that,
yeah,
at that time we cannot do this linearized gravity approximation. So the amplitude of the gravity waves will not be the same as you portray.
So even at that point, the amplitude of gravitational waves were actually small, okay, but what happened is that those small fluctuations got kind of frozen, because the universe started expanding so rapidly that the wavelengths were stretched beyond the horizon size. Okay, the horizon did not expand that rapidly. So now what happens is that for wavelengths which are longer than the horizon size, they have to be frozen, because otherwise you are violating causality. Now when at some point they came back, so the amplitude remained the same. So this is why they are still, I mean, their strength kind of persisted, and after that they are freely flowing. Okay, there is nothing, they are not getting absorbed or anything like that. Okay. Okay. So now coming back to, but there is a lot of literature there, like about this fluctuations in the early universe, that what would be what is called the scalar to tensor ratio and so on. So basically there is a scalar density fluctuations which is known, but the tensor fluctuation, that is which is the gravitational wave part of it, is actually like at present what we believe is 0.1% of the actual density perturbation. Okay, now coming to the most what is that called? We say promising, or rather is the source which could be modeled most accurately and has been detected in gravitational wave detectors. So you see that the picture I gave you in that stretched rubber sheet. Okay, what happens is that these objects go around, and then when they are going around, they create gravitational waves because the overall quadrupole moment is changing. When gravitational waves carry energy, and this can be explained with a thought experiment that if you take a rod and you put two beads on the rod and gravitational waves falling on that, because of gravitational waves, these beads will feel a tidal force, okay, which will make them slightly move on the bead, which is going to create some heat, and that heat, the only source of heat is gravitational waves, which means that gravitational waves is carrying away energy. This is, I think, Feynman's thought experiment. So now if gravitational waves, this system is losing gravitational waves, to compensate, meaning energy through gravitational waves, to compensate for that loss of energy, the objects have to come a bit closer. Okay, when they come close, they start moving at moving faster, because as you know, the inner planets move faster than the outer planets, because the period, this is like Kepler's law. So which basically forces the system to lose energy at an even faster rate, because the rate of change of quadrupole moment increases. It goes as frequency square. Okay, so in the end, it is basically an avalanche process, where at the end of the process it starts losing energy at an extremely fast rate. Okay, and until they merge. Just to give you an idea of how much energy is lost in this process, is that the first detection that has happened, the masses of the initial black holes were 29 and 36. The final mass is around 62, which means that 3 solar mass worth of energy was lost through gravitational waves alone. Okay. Now if you look at the sun, in billions of years, sun has lost about 1 or few percent of its energy, okay, which is like a percent of a solar mass. And here we are talking about 3 solar mass of energy radiated out in in this binary merger process. I mean, of course, it is losing energy for the whole period of evolution, but if you consider a good fraction of it going out in this last final merger state, you can imagine that what kind of energy was released in this process. So these are now coming back to this part. So you see that this part, the in spiral part, is when they are just going around each other. Okay, this can be modeled very well. Even with quadrupole formula, you can get a good estimate of that, but that is not going to be sufficient, because when the signal which is detected is when the black holes are sufficiently close, and there you have to take into account all this non-linear effect. So what people do is that there is a post-Newtonian theory which is used, which basically adds perturbations to the okay, there are questions coming, but I think I will take them later on. So so what happens is that these perturbations are expanded in powers of V by C, and more or less it is if you go up to 7th power of V by C, which is called the 3.5 post-Newtonian expansion, you get reasonably accurate waveform. Okay, this work was a significant part of this modeling was done in India with Bala Iyer and his group in RRI. The final part is when the final black hole which is formed. See, the event horizons are coming together, and then there is a common, let's say, horizon which forms, and then, but that has a very arbitrary shape. It is not like a symmetric black hole. Then it starts radiating energy because it is like a moving, the quadrupole moment keeps changing, and at some point it becomes a more symmetric black hole, and this is basically through a process called ring down. It is like a damped harmonic oscillation. Okay, And this part also, a significant amount of work was done in India by C.V. Vishweshwara, that is in early 1970s. Of course, these things evolved much more afterwards. And the interesting part here is that these damped harmonic oscillation modes would be a function of only the final mass and angular momentum of the black hole, and that would be a very interesting test of general relativity. This is basically something related to the no-here theorem. The central part here, where a lot of energy is emitted when the event horizons are really close, has to be done through numerical relativity, and this part was lacking in India for some time, but now there are people who are professional numerical relativists who are doing these binary black hole simulations in India, in ICTS, like Prayush Kumar and company. They are doing this kind of part. Fine. Now, if you look at these numbers little bit, you see that there are two ways of writing this. This is for a large in-spiral part where the period is like 1 hour or so, and but the source is very close, so where like two things are going around. The problem is that the probability of finding such sources is extremely low, okay, in our galaxy. But this one is what is detected. So here you can see that if the binary has two 1.4 solar mass neutron stars, and the frequency is like 100 Hz, that is 1/10 milliseconds, and it is about a megaparsec away, even though sources are not really a megaparsec away, they are much farther away, but the masses are also higher. So altogether you get about 10 to the minus 21. Now I will just show you an animation in case it becomes little better. You see that these two black holes are going around, they are emitting gravitational waves, and here you see that as they come close, their period increases, which means that the wavelength is reducing and also the amplitude is increasing. Okay, you see that in the last moment it increases very rapidly, and this also happens for bird chirp sound. So which is why this is called, the first part of the signal is called the chirp signal. Okay. So now coming to the detection, I'll just let me see. Okay, you have already mentioned that. So now if you see this is a cartoon of the first detection. I have already told you about that. So these 29 and 36 solar mass black holes went around, merged and formed a 62 solar mass black hole. The signal which is predicted in the previous slide, what we see, you see that this kind of signal which is predicted from simulations was observed in two detectors in the United States, this red and blue. Can we turn off this light? So you see that the signal has kind of a very similar shape, the red and blue, and they were detected in two detectors almost at the same time, and the detectors are 3,000 kilometers away. So the probability that such a signal would be generated in two detectors at the same time which are so far away was 1 in 65,000 years. So you can safely say that this was a detection of gravitational waves. For this detection, Rainer Weiss, Barry Barish and Kip Thorne got the Nobel Prize in Physics in 2017. Though this was a remarkable international collaboration, more than 1,000 people across the globe contributed to this effort, and you can see there are many dots in India. I have already told you the contribution from India in the source modeling part, but also it involved mathematical techniques to extract the signal from data. Okay, a lot of that work happened at IUCAA under Sanjeev Dhurandhar and his students and postdoc. Patrick was one of them. This was 30. 90s or 30 years ago. I think most people here were not born at that time when this. That is. Okay. All right. Also, there was a lot of effort in identifying the glitches in the signal. It is, even though we had mostly concentrate in lectures on the source part, like signal part, but a significant amount of challenge is to deal with the non-ideal parts, where the data is constantly getting glitches, okay, which are like some bursts of signal, like what should I say, objects in the data, and you have to identify them, isolate them, and say that these are glitches and this is the true signal. Prussia works on those things, which are this exercise is known as detector characterization, and there is a whole many things which happen in detector characterization. Then there are also the Indian astronomical community significantly contributed to the follow-up of the sources which were observed, and I will come to that later on. The experimental part was somewhat lacking in the early days, but now with LIGO India in the horizon, those have also picked up. Okay, since I have mentioned about it, only I see that Anuj is there. He works on those source modeling part with more microlensing. Oh, but you also worked on eccentricity?
Not in development of eccentric binaries.
I mean, that is fine. I mean, you were involved in that eccentric binaries, like where we try to see how much deviation is coming in the signal. See, right now, when we get the signal with very, first principle was to make, first approximation was to consider a simple system. But then now you want to try to get to more details like eccentricity, precision, like that is the spins are not aligned, okay, then all those things. Okay, anyway, I will come to some of this probably later on, maybe, let's see how much time permitting. The next big thing that happened in the detection is the detection of the binary neutron star merger GW170817. So that means that it was detected in 2017, August 17. Okay, this was because these are binary neutron stars. They could emit. See, black holes don't emit any electromagnetic radiation, but binary neutron stars can. So they emitted electromagnetic radiation in the whole wide range of frequency bands. Okay, starting from gamma ray, X-ray to radio, and it was observed for weeks by various observatories at various times, because when you get what radiation depends. So NASA made this very nice animation, and this is very informative also. You see that two neutron stars are going around, they are emitting gravitational waves, and then they collide, and then this prompt emission comes from the core of the collision, and then a jet comes out which hits the interstellar medium, causing the afterglow. And this whole thing looks very trivial now after the detection. These kind of things were predicted, but only after this observation, through multi-wavelength observations, people could confirm that yes, this is really the picture. Okay, there are many possibilities. Often what happens in observations is that there are various possibilities. Only after a detection, people claim that I predicted this, but that is true, but there are 10 more predictions. So this is something which we have to keep in mind. One very important thing that has happened with GW170817 is that is constraining the speed of gravitational waves. Okay, let me tell you what the problem thing is. See, general relativity is not the only relativistic theory of gravitation. There are other theories, but general relativity has so far passed all the tests. Okay, and self-consistent with other branches of physics and itself. Now the thing is that, but we have to keep probing. Okay, now, general relativity predicts that gravitational waves travel at the speed of light. So you need to test whether that is true, or at some point it breaks down and there is a little bit of mass associated to gravitational waves. Maybe if there are gravitons, then maybe gravitons are massive or whatever. There could be dispersion and so on. So what happened here is that assuming, see this is the sound of the chirp signal, and that ting is just an artificial alert. So from GW170817, a signal came at some point of time, okay, and you see it is relatively easy to identify the location of the signal. It is very accurate actually to find the exact time of merger from gravitational waves. And in the Fermi satellite detected the gamma ray burst, the signal from the gamma ray burst 2 seconds later, okay, and these 2 seconds can probably be explained by propagation delay, like because it's a dense environment, so photon takes some time to travel, and also the afterglow also the prompt emission might have released little later, or we don't know the exact model, what exactly happened there. But assuming that these two happen almost at the same time, and that these waves, both of these, traveled some 3 into 10 to the 15 seconds, tells us that the speed of gravitational waves and light in vacuum differ at most by 1 part in 10 to the 16. Okay? This is a very strong constraint. Of course, there are many theories saying that how do you know that they started exactly at the same time, etc. This will require many more mergers to confirm. But this already gives you a very strong constraint, probably it is going to be true. So now if you want to come up with a different relativistic theory of gravitation, you would be tempted, you would be strongly encouraged, let's say, to satisfy these constraints, that it should not, you should not produce more delays or more mass. The next thing we learn is, this is just to show you that how the neutron star signal compares to the black hole signals. Neutron star signals are very long, okay, this is like a minute, and these are usually a second, okay. This is the main difference between black hole and neutron stars, which actually, which is one of the reasons why matched filtering technique, which I'll show you later on, is more important for this kind of signals, because they are very weak, but there's a long phase evolution is involved.
To ask them why is it that signals are shorter than
I don't see anybody asking questions, so I thought they already know everything, or already I am such a good teacher that everything is understood. Both are like win-win. So can somebody tell me that why the black hole signals are shorter, but the neutron star signals are much longer?
probably from 50 hertz to 1 kilohertz.
In that band of the in the band of the detector. So this left hand side corresponds to, let's say, when the period of the binary is, let's say, 30 hertz, okay, and the frequency is always increasing, okay. For the black holes, they merge much more quickly, but for the neutron star it keeps going. What could be the reason?
Energy density is more for a black hole. Energy density for a black hole system is more.
Energy density for a black hole is actually comparable to a neutron star, especially for bigger black holes. For 10 solar mass, I think they will be very much comparable. Smaller one, 3 solar mass maybe more, but not for 10. Black hole mass is proportional to the radius, right? And the density is 1 by r cube. So actually black hole's density fall as 1 by r cube. Bigger the black hole, smaller the density. Any other guess? Okay, I can give you one hint, that the frequency evolution of all the binaries are very similar. They follow almost like, if you plot all the binaries in the frequency, they follow almost parallel lines, okay. So it is like almost linear, on a log scale you will see like there are these parallel lines. So these are merging early means that they merge at a lower frequency. So why black holes merge at a lower frequency? That is the peak frequency before merger is much lower for black holes than neutron stars. I have actually already given you the answer in the first part of the talk. There is something I said when I was talking about these bodies going on the stretched sheet. Something happens. What is that? I will be like this salesman that you see in the train, that you first pick out one set of comms. You say that, oh, well, this is 10.
One hint has to be given that the black hole cases, the mass of the black holes are much bigger than the neutrons.
That is true. So it is like tens of solar masses. And here it is like 1.4, 1.4. Total is 3 solar mass, let's say. So that, now I give more hints. And like, let's see if there is a buyer. So 2 things have been told. These are much heavier. The initial frequency is anyway the same. And that this one merges at a much higher frequency. That means the period of this is much smaller than the black hole ones. Okay. They can reach a much smaller frequency. A much higher frequency, that is a much smaller period. Yes. Schwarzschild radius. So the radius of a neutron star, okay, 1.4 solar mass neutron star is almost the same as a 3 solar mass black hole. Okay. So but I mean, you are in the right direction though, but that is bigger, much bigger for a 30 solar mass black hole. So the Schwarzschild radius for the radius of a 30 solar mass black hole would be probably 10 times the diameter of a neutron star, which is, let's say, 10 kilometer. So what does it tell you? That is actually the reason. Okay, the thing is that they touch so when they touch, then they cannot go around anymore because there is a common horizon or trapped surface has already been formed. So now they cannot come out. So that is the end of the merger. Okay. So if the object is bigger, then they touch quicker. And the thing is that from Kepler's law we know that if you want to have higher period, then you have to come closer and closer. Then the period actually reduces, lower period, higher frequency. I'm mixing up this thing. So the inner planets have smaller period, right? And the Earth has 1 year, but the planets which are closer to the Sun has lesser period, like from Kepler's law. So that is exactly what is happening. Okay, because the black holes are big and they merge, they touch each other early, the distance at which they merge is larger. I mean, the scaling is little more complicated, but it's essentially that is the reason.
Sanjit, there are some questions on chat. We want to take it now.
Okay, so let me see. What could be so first question is, what could be these 2 polarization states of gravitational waves? Linear or circular or both? Yeah. Let's say generally it could be circular polarization. I mean, unless you look at a system which is generating exactly the plus polarization, which will happen in a certain situation. In general, it would be a mix of both the polarizations. What could be these 2 polarization states of gravitational waves? No, that is what I said. We have the initial GW detection for so Vinu's question, Vinu Vikram, that we have the initial GW detection for less than 1 second. Why is that a short period? A galaxy can always be observed if we detect that in the early universe. And yeah, the problem is the lower frequency cutoff. Even though the black holes are moving for a very long time, they enter the frequency band of the detector less than a second before merging. So that is like 30 Hz. I hope that is the question you are asking. Then a question from Dr. Parag Bhattacharya is that could the presence of gamma ray signal after the chirp be explained by the production due to some other high energy process instead of a, well, there are many people working on this, and many theories, like many simulations have been done, but this is one possibility, is that it's a dense environment. So even if light was emitted just before the merger, I mean that is more than 2 seconds, not more than 2 seconds before the merger, but what I mean is that the tidal disruption etc. happened before the merger, even then it can have some delays. But these things are, it will require a lot of simulations, lot of observations, and then we will know.
Optical depth, electromagnetic.
Optical depth is high, yeah,
Optical depth.
yeah,
They
pass through the matter. Now, the last question is that Ahibam Kisharjit Singh, isn't the inspiral time related to power dissipation in gravitational waves? Yeah, meaning it is, they go hand in hand. The power dissipation in gravitational waves lead to the objects coming closer. Okay, but this is sort of sacred. It is not like it does not depend really on the material or anything. It is just mass dependent as dictated by general relativity. Okay, I'll move forward.
Why did you say that we require the post-Newtonian formalism?
So the thing is that this quadrupole formula is valid only in a certain situation when the objects are moving slowly. This is very similar to dipole radiation in electromagnetic theory, which is valid actually in a certain limit. Dipole approximation is not valid when the system is moving, changing its configuration very quickly. Same thing here. So when, but the detection is happening when the objects are very close. So there the system is changing its configuration very quickly, and the quadrupole approximation would not be valid. Well, it will break down. It will give you a good estimate of the amplitude, but you need to start putting all these other corrections there. So which is why you need to put these post-Newtonian corrections. Acha, that water is okay. This is not more than a month old, right? So I have to. No. This is fine. No, I am not so much sure about the bottled water. This may be safer. But I am just being careful.
With regards to the first comment on the Zoom that you answered, where it becomes visible only close to the margin.
Yeah.
That is only with ground-based detectors, right? If we had space, then you would be able to observe more part for the
That is not completely true, because the space is still, I mean, when we are talking about space-based detector, it is still very close to the earth. So signal has to arrive at the earth. But what is, since we are discussing this, decihertz, right? Space-based, right. That is what the thing is that if we could get early warning, that would be the best. Because then in that situation, we would be able to see what happens before the merger. Right now, whatever is happening, all this electromagnetic follow-up is happening after the merger. The gamma ray, of course, we have no control on, because that is happening right around the merger. But what she is saying is that if we need that early warning, if we need to observe what happens before the merger, well before, if we go to space like the decihertz detector, then we can get an early warning well in advance, so that all the electromagnetic observatories could point to the location where a merger is going to happen. I will come to that towards the end of the talk. I think there is still some time.
So if the black hole is of the same size as a neutron star, will this happen?
If the black hole is of the same size as a neutron star, which would mean it is a 3 solar mass black hole essentially, then the signal would be of the same size, same length.
So basically the length of the signal is a direct mapping to the mass of the black hole.
It is, yeah, it is all little bit problem is there, because you see, it is not just the distance. Even though I am saying that, the mass also matters, okay? Because the black holes will have twice the mass, the period will be lesser for that mass. So it will be not exactly the same. It will be little smaller, but still a long signal.
Neutron star will be direct interaction between the matter between those two stars.
So the tidal interactions don't change. See, this up to this part, this is mostly gravitational. Only in the last few cycles the electromagnetic interactions come into the picture. Before that, even though there is tidal distortions happening, what tidal distortions will do is to change the waveform somewhat, but not dramatically change the whole waveform.
So the related question for only the black hole signals, GW15-26, why is that on the longest? Is it the lowest masses or?
Yeah, the masses, this is like completely based on the masses. That is the thing.
I don't understand fully like why it is, like you explained, you have lower mass in neutron star and higher mass in black hole.
Correct.
And that's why you're getting smaller. But like this radius of the black hole is actually very smaller, right? And so it is very compact.
Radius of the black hole is not smaller than neutron star. It is only for up to 3 solar mass. 1.4 solar mass neutron star has a 10 kilometer radius. The size of a what is the size of a black hole with 1 solar mass? Even though they don't exist, it would be 1.5 kilo. 3 kilometers. So 3 solar mass black hole will have 10 kilometer. So that is why I'm saying the 3 solar mass black hole and a 1.5 solar mass neutron star have same size. But that is because but after that, when you go to 10 solar mass black hole, then it is 10 times that is 30 kilometers, which is much bigger than the neutron star.
And you cannot have neutron star that.
And so basically, okay, let me tell you this way, that neutron stars are almost always smaller than the black hole. So far, according to our understanding, the point is that the black holes that we have detected are all 3 solar mass and above, so which is like 10 kilometers, okay. However, we cannot rule out the possibility of detecting smaller black holes. There could be primordial black holes and so on, which are 1 solar mass. But other than that, whatever we have observed in astrophysics, neutron stars are almost always smaller. I mean, it is not exactly like, a 3 solar mass black hole would probably be 9 kilometer, not 10 kilometer and so on. But other than that, it's the same.
Yeah, so far no neutron star with mass greater than 2.5 solar mass has ever been observed.
Yeah. That is the thing. Even though I don't know the size of the 2.5 solar mass neutron stars, whether it is smaller or not, I don't know. For 1.5, I think it is 10 kilometers, because it is strongly dependent on the mass, radius, basically the equation of state. When you evolve, equation of states are also very different. I think Parisi worked on those, right? Swarnim worked on, So those things are very complicated. I mean, it is not very easy to say, but more or less whatever you are seeing here, they are all bigger than neutron stars. Okay, let me move forward. So the thing is that what all did we learn from this single GW170817 is simply amazing, okay. With one binary, we came to know that this picture, that these binaries go around and create like all these things. This short GRB picture was validated. Then there are already some constraints on neutron star matter which could be put, even though a lot of observations are done, because there are hundreds of equations of state. Then there was a constant put on the speed of light. Then I will show you very soon that there are indications that all these heavy elements which we are using here, like gold, silver, etc., significant part of it was actually produced in the binary neutron star mergers. Then we got an independent estimate of Hubble constant. This is the one which excites me the most, because I also do cosmology. And the thing is that I will not have time to get into the deeper details, but you see that we have 2 very precise measurements of Hubble constant. One from CMB, which is shown in this green band, it is around 67, and the other in this orange band, it is with from supernova observations, near low redshift observations, which is like 73. These are both claimed to be very precise, but they don't match. There is a gap here. You see, they are basically distinct. So at least one of them is wrong, or our understanding of the universe in the late times and the early times requires modifications. Now what happens is that you see these dotted, these dashed lines, this measurement came from gravitational wave, okay? You get the luminosity distance from the chirp signal, from the gravitational wave signal, because we know we get the masses from their phase evolution, which tells us what should be the amplitude, and since the amplitude scales as 1 by r, from there we know what should be the luminosity distance. And since this object could be localized on the sky, we came to know about the host galaxy, and that gives us the redshift, because once you know the host galaxy, you can do spectroscopy and get the redshift. That gave an estimate of Hubble constant. But obviously you will say that this error bar is very large compared to what we need. That is true, but this can be stacked. That is, if we have about 50 observations of binary neutron stars, we will be able to break this degeneracy. That will be one of the primary outcome of LIGO India. I will come to that. I have now created the whole stage for the need for LIGO India, and we will soon get into that.
So, this is a point probably. What you say is that from gravitational wave we can also have a measurement of Hubble.
Yes.
And that is the dotted line.
This is the dotted line. You can see, look at this plot also. This is the year, and this is the Hubble constant measurements from various observations. These blue ones are from predominantly from supernova, and I think the Cepheid variables, etc. And these ones are from CMB, this red and green. And this magenta one is from gravitational waves. And this is going to shrink.
So earlier I heard that we could not locate the pinpointed exact location of the merger, but now we can.
We could for this particular source, GW17817. So far, only one event could be followed up in the 10 years of gravitational wave astronomy, and that is because this event happened only 40 megaparsec away, which is very rare, which is why it happened. But we will see why. This is precisely the reason why LIGO India is so important, because we need to localize more sources. If we can localize them better, we could have deeper observations. Then hopefully we will get more and more follow-up. This is the idea. Okay, so I just wanted to show you this interesting fact that you see that this is periodic table, and the bright yellow ones are coming from merging neutron stars, and you see many of these elements like gold, there is silver somewhere above that, Ag here. So all those things are mostly created from binary neutron star. I can see many people are using gold, silver jewelry. So those who are actually forming binary neutron star mergers, and at least a good chance. Here is the now where we are with first, let's say, almost 10 years of gravitational wave astronomy. This now looks trivial, okay. And I was giving a lecture in 2015 in this room, and the question was at that time was that what if LIGO does not detect a gravitational waves? And I said that that will be absolutely wonderful. The thing is that we are using the same instrument, that is Michelson interferometer, whose non-detection completely changed physics. Similarly, that instrument can do a miracle again, that it did not detect gravitational waves, so we have to completely rethink general relativity. Fortunately or unfortunately, that did not happen. We did detect. But you see that the first detection, at that point, the main people are very skeptical whether we are going to detect or not. And now we have this 100 and it looks very trivial. But this is not, I will show you, if there is time, that how non-trivial this is. I will come to that all the detections were, let me see if I have something here later on, which I can show you that how, okay, maybe like I can tell you right now, okay. The thing is that the rate which was predicted for LIGO so there was an initial LIGO which was basically built as a technology demonstrator, and that operated from 1995 to 2005. Okay, and then when in principle it was shown that it can achieve enough sensitivity, then the next advanced detector was built. Okay, this was interestingly was all proposed by Kipthon and Ray Weiss and company. They envisioned all these things. Now the rates which were predicted for advanced LIGO for various neutron star mergers and black hole mergers was like this, that with advanced LIGO we will get 40 binary neutron star mergers every week and 20 binary black hole mergers every week. Now what has happened is that, which means that we will get a factor of 2, twice the number of binary neutron star mergers than the binary black hole mergers. At this point we have 100 confirmed detections of binary, about 100 black hole mergers, and we have only 2 binary neutron star merger detections, one of which was followed up, which means it is 2%. The prediction was factor of 2, we get 2%, that is 200% versus 2%. You see, there is a factor of 100 discrepancy. So even though this is basically, this shows all the detections that has happened, their masses, etc., and it does not look so glorified, but the physics behind, it has completely already dramatically changed our understanding of astrophysics. We now know that lower mass binaries are very difficult to detect. It is not because their signal is any different, but that the probability of their detection is extremely low. Probability of finding them in the nearby universe is extremely low. And this is probably because of the reason that these binary mergers, this is one of the theories, which is one of the primary theories, that these mergers are probably happening in star clusters, okay, where all these objects are coming closer and closer, heavy objects, and that is because there is, let's say this is a thermalized system, there is equipartition of energy. Smaller the mass, higher the velocity, and these smaller objects are getting kicked out, and the rest carrying energy from the system, and the other ones are slowly, the heavier ones are retained in the system with the same energy. So they are basically, this is called a mass segregation. So more massive objects are remaining in these star clusters. So we would find more heavier objects in the nearby universe. The lighter objects in those star clusters are in the earlier part of the universe. Okay, but it is not that their numbers, so it's more complicated than that, subtle than that. It is not that the number of new binary neutron star mergers are actually less than the number of is less than the number of binary black hole mergers, but binary black hole mergers have higher amplitude. So what happens is that we can see them at a further distance, okay, from a distant universe. But the binary neutron star mergers, the lower mass ones, even if the number is slightly more than the other ones, they can be visible only when they are close enough. So basically what has changed is that we initially thought the number is much larger than the higher mass ones, but that is not the case. Okay, their number has significantly fallen. That's number of smaller mass or let's say few solar mass objects have significantly fallen in the star clusters, which is why we are not detecting enough, and we need next generation detectors if we need to detect those a large number of those smaller mass objects.
So does this include the lensing effects because of the degeneration of light, because they are so distant?
There could be lensing, but lensing probability is only 1% right now, 0.1%. Okay, so lensing would not be able to increase the population so dramatically. It can enable you to detect one or two outliers more like, but not full this. increase. But of course, if we go to very early universe, then maybe the chances of lensing will go up. But the primary thing is coming because of the population is simply higher, meaning, again, you will see like what I mean, okay. Okay, so now the thing is that, let me go forward, and so this is the present status. Like there are about 203 detection candidates, which many of them may be detected, and there are about 4,000 low significance events which are not claimed to be detected. Acha, there is a question. Let me see. The question is, one possible explanation for the time lag between the GW of GW17817 is that the model of short GRBs say that the gamma rays are emitted by the shock waves in the relativistic jet from the merging neutron stars, which is, meaning the jets are formed little later. So this is also highly possible. But the idea is clear that there is a lot of work to do, and like these are basically a list of many. I mean, there are many unresolved issues. So this is basically, we are at a stage of the first detection. Okay, it is like that Galileo's time that Galileo has detected, like seen only few planets. We don't know most of this, their astrophysics, like where, when, and how do these black holes and their binaries form is not known. There are some competing theories. There could be a common evolution, common envelope evolution, etc., etc. Which redshift they peak, etc. All those things are still a problem. People still cannot form black holes confidently, in the sense that they don't know what it is. It is difficult to bring two objects together and merge. Like the Earth is going around the sun, and it is not going to fall in the sun. Okay. Similarly, there is a problem that bringing the objects together is not so easy. It can happen in dense clusters where there is some dust, which can provide some drag, so that these things can dissipate energy at a faster rate and so on. So these are open questions. How many such binaries are universe? We don't know. What is the distribution of their masses and spin? Whether there is a power law, whether if there is more spin. For example, generally the black holes, probably I would feel that they would have more spin because they are forming in an astrophysical situation. But these things have to be probed, that whether if they are primordial in nature, then probably the spins could be less. Then how are they distributed in distance and direction? Is it isotropic and so on? So distance would basically mean that where the star formation peaks and how much time it takes to form them. What are the properties of neutron star matter? Basically equation of state, etc. How massive can a neutron star be? To be very precise, can there be a 3 solar mass neutron star or a 2 solar mass black hole? We don't know this yet. For example, the most interesting question is that after GW17817, which was 2 neutron star merger, right, 1.4 solar mass each, and neutron star masses are very strongly, most of them are in that range. So most of the mergers that will happen will be in that range. Okay, maybe some mass will fly away, but the final mass, final object, what is that? Is that a neutron star or is that a black hole? Because it is very likely that the final mass is more than 2.5 solar mass. We have not seen any neutron stars more than 2.5 solar mass. But we have not seen any black holes also which is less than 3 solar mass. So what is that object? So and so on and so forth. And since we have a lot of gold here and silver, so you know that binary neutron stars mergers have happened, quite a few. The question is that what their remnants are is not known. Now, do black holes exist in this range? This is also very interesting because there are these huge black holes which you see at the center of the galaxies. Okay, how did they form? Did they start from a very big seed black hole and that grew, or there are collisions, mergers of smaller and smaller black holes which hierarchically grew to these big black holes? This is not known. And then, of course, general relativity is the ultimate theory of gravitation. If it is not, probably it will show some deviations in the waveform, in the ring down phase, etc. What is the correct value of Hubble constant? So many of these are unknown questions, and probably a lot of gravitational wave detections are necessary to partly address this question. This has to be done along with the electromagnetic observations and neutrino observation and so on. Okay, now moving a bit faster, you see that there are gravitational waves sources predicted in various frequency bands, and many probes are there, direct gravitational wave detector, space-based detector, then DESI also people are planning, then the pulsar timing array which can probe gravitational waves. If there is a radio astronomy, I'm sure there will be lectures, so they will certainly tell you about the goals. I don't know whether they are there. Somebody is covering radio astronomy, GMRT. So you see that when you look at the pulsars are very precise clocks, and when gravitational waves pass through them, they can create a small jitter in that arrival time of the pulsar, which would be actually smaller than the jitter anyway you see. But again, that jitter will be correlated across the pulsars, and by correlating that you may be able to detect gravitational waves, and there is a strong evidence which was recently found a couple of years back, and hopefully they will get a full 5 sigma detection in the next few years. Okay, and of course the stochastic background that I talked about from the early universe creates a signature in CMB B mode polarization, and by detecting that signature in CMB we may be able to detect gravitational waves. Okay, so but the challenge there is the foreground, that the galactic dust also creates such a signature. So the primary challenge is to distinguish which part is coming from our galaxy and which part is the primordial signal. So basically the point is that we are right now here in gravitational waves. This is like Galileo's telescope, and you see in 400 years we have gone quite far in electromagnetic observations, and we have to do the same in gravitational waves. For example, we have to create, you see these are the sky maps in electromagnetic observation starting from radio to gamma ray. One day we will probably get that. I mean, there is a lot of time. We should not be worried about. This will be difficult to expect in our lifetimes. All these things will happen, but it will. We should feel good that we are part of this journey. So now coming back to the next stages. Okay, now I have been very slow. So now in the 15 minutes I will take. Okay, even though there is a competition between hunger and your brain, but let's see how it goes. So the point here is that we have to build a network of detectors, we have to improve sensitivities of the present detectors. We cannot observe all the gravitational waves from the Earth because the seismic noise at lower frequencies cannot be beaten. We have to go to space to detect even larger black holes whose frequencies are even lower, and so on. But for us, of course, LIGO India is the most important thing. Now let me give you very quickly about detections. You see, the first detection happened, indirect detection happened by the observation of this binary pulsar, which was again like emitting gravitational waves, so its orbit was not exactly closing, so the periastron was slightly moving. By observing this over several decades, people found that these dots, this how the periastron time is shifting, and this line, which is the prediction from general relativity, which basically showed that that gravitational, the prediction how the system is going to behave if it emitted gravitational waves exactly matches, consistent with general relativity, and this gave the Hulse-Taylor a Nobel Prize in Physics in '92, I think. Now coming to the direct detection, that H that we derived before, what is the interpretation of the H? Is that, as I said, that if there are free masses, then it will create a distortion like this. Suppose there are free masses in this circle, gravitational waves are falling on this slide, then it will create this area preserving sort of distortion to the first order, and the plus polarization will move it like this, and the cross one will do it like this, so which is why it is plus and cross. Now the thing is that basically it is nothing moves, it is the light travel time which changes. Nothing moves in the coordinate frame, but you can measure the tidal force which is applied by the gravitational waves between two freely hanging masses. So one way to do it is using, you see, you can put a bar and then the bar can get resonated. That was the first attempt to detect gravitational waves. It is like it's a resonant bar. So when the gravitational wave pass and then the frequency matches for a short while with the resonance frequency of the bar, it creates an oscillation in the bar. The problem with that detection is that being a highly resonant detector, the bandwidth is extremely small, and since the signal frequency is changing, you observe the signal for a very short time, so you would not get enough signal to noise ratio. And there are many other problems also. It is not omnidirectional, etc. So the probability of detection goes down. But what is the best method so far is using laser interferometry. You put so I will have a animation there, but the main thing is that when gravitational waves fall, this one arm becomes smaller while the other becomes larger. Laser interferometers are very good in measuring arm length differences, okay, and that is why we can detect so small fluctuations which are smaller than the size of a proton, okay. Now, so how it is exactly done, I will tell you later. So this is the bar detector which Joe Weber created. Even though this did not detect anything, Joe Weber is still considered the father of gravitational wave astronomy, because everybody told him not to do this because this is impossible to detect gravitational waves. So even if his effort did not succeed, his effort succeeded in pushing the field for the final detection. And this is how the Michelson interferometer works. You see that there is a beam splitter, light emits from here. I will show you slowly. So beam splitter splits the light in two parts. Then it hits the mirror, okay. It comes back and then gets recombined. This you have seen in any Michelson interferometer. And if the phase is opposite, then you will get a dark fringe here. They will destructively interfere. But if the arm length changes because of gravitational waves, then it is not perfectly destructive interference. So you will have fluctuations here if you put a photodiode. And that is how gravitational waves are detected. Even though this is a very simplistic picture, this is not exactly how it is done, but we don't need to get into those details right now. So this is a laser interferometer, and this is in Hanford. Okay, this is 4 kilometer arms. Okay, now the thing is that why 4 kilometer? Why such a big detector? The thing is that H which we are trying to measure is produces a strain signal. So longer the arm length, you will get a higher fluctuation. But more complicated thing is that when you look at any, let's say, dipole antenna and so on, the length of an antenna for optimal detection is actually lambda by 4, and that applies here also. Otherwise, what happens is that if you observe for too long, since the gravitational wave frequency is also changing, it is going to wash out the change in the arm length. So you have to observe for periods significantly smaller than the period of the signal. Okay. So, and if you observe for a too short of a period, then you are losing signal to noise ratio. So typically, the length of the arm length should be lambda by 4, so that the total path length is like half the cycle, okay, maximum. But the signals which we are detecting are at 100 Hz of around that frequency, which would mean the arm length should be, the wavelength should be 3000 kilometer, which means that the arm length should be 1000 kilometer. But 1000 kilometer detector you cannot practically make on the earth, okay. So what is done is that the one way is that you could put big mirrors and do multiple reflections, but that would be extremely complicated design, and every reflection would lead to losses. You need very large optics and so on, because you need about 100. So you have got 4 kilometers, you want to make it 1000 kilometers, so you need 200 to 300 reflections. That would create an enormously complicated design. So what is done instead is that you put another mirror here and put a Fabry-Perot cavity. Okay. In a Fabry-Perot cavity, based on how you choose the reflectivities, lights get trapped and they keep bouncing back and forth. and it is chosen in such a way, it's called the finesse, it's chosen in such a way that approximately 200 to 300 times light bounces, making the effective arm length around 1000 kilometers. Okay, now, so actual thing is very complicated and it has to be, so basically our primary problem is the seismic noise. The vibrations on the earth finally come to this hanging mirror through the suspension point. So how do you reduce that? The thing is that that is the reason why it is suspended in the first place, that if you have a pendulum and you slowly move the pendulum, you will see that the pendulum is moving with your hand, right? Now imagine that the pendulum, you move your hand very fast. You will see that the pendulum, you can imagine, does not move so fast. You can imagine a stone with a thread, this thing. So basically, from the theory of simple harmonic oscillation, everybody has done it here, forced harmonic oscillation, you know that you see this picture like where there is a resonant peak and the higher frequencies go down, this fall as 1 by f square. So basically a pendulum acts as a high frequency high pass filter, the lower frequencies are blocked. So which is exactly, sorry, it's a low pass filter, higher frequencies are blocked. So all the high frequency seismic waves are blocked by a pendulum, and if you put 4 stages, each stage adds a 1 by f square factor, so it becomes a 1 by f to the power 8 fall off, which is how you get a seismic barrier like this. But even then, even with all this, you cannot really go beyond below few hertz. Okay, it is impossible to beat the seismic signal below that frequency. At the higher frequencies, it is dominated by photon shot noise. Okay, this is basically the same noise which comes when we take pictures with digital camera. That is why it gets blurred in the night, because the number of photon becomes smaller, so it will be noisy. But if you want to increase the number of photons, it integrates for a longer time, so it becomes blurry because of hand movement, etc. But anyway, you need to increase the laser power in this frequency band in order to reduce the shot noise part. But then you would say that why it is not increased indefinitely. The problem is that this laser, whenever you put laser power on something, it is never a constant power. Even though it is a continuous wave laser, there is Poisson noise. Okay, so it fluctuates. That fluctuation causes fluctuations on the pressure that is appearing, that is exerted on the mirror. Okay, so the pressure is not the problem, but the fluctuation in the pressure is the problem. So that radiation pressure noise will start dominating at this range if you start increasing the power here. So in order to reduce the radiation pressure noise, then you have to increase the mass of the mirror, because the acceleration noise is force noise by mass. But then if you want to increase the mass, then you have to change the suspensions, because the suspensions are made of glass. It has to be of the same material to reduce noise. Then the glass has to be changed. Okay. So basically what I mean is that if you want to change any of this, the whole system has to be revived. So which is why it gets so challenging. And also one more thing related to radiation pressure noise is that I told you that we need a 1000 kilometer detector, but we have only 4 kilometer detector. So we increase the finesse to reduce the arm length. You could also ask, which surprisingly we did not ask, that why we don't increase the finesse by factor of 1000 and then make the detector 1 kilometer. That is not possible because of exactly the same reason, that when we try to increase the finesse, the radiation pressure noise multiplies. Okay, because the number of bounces increase. So because of the same reason, we cannot make the detector too small as well. So that is the situation. Now these are the 2 detectors in the US which are 4 kilometer. These are the LIGO detectors, laser interferometer gravitational observatory. There is a detector in Vargo which is 3 kilometer, which is also sensitive but not as sensitive as the LIGO detectors. Then there is a geodetector which is 600 meter. A lot of technology development for the LIGO detectors happen there, and which is why this is an interesting place to work. And then there is a detector in Japan which is operating, but they have a different technology. They go underground. Then there is cryogenics to reduce the Brownian noise on the mirror surface, which dominates the central part of the sensitivity. With reduction in temperature, you can reduce that. but their sensitivity is right now very low. And then hopefully there will be a detector in India operating by 2030, and that is what it is about. So why do we need a detector in India? Now this is the main question. You see that with 2 detectors you cannot localize the source. So this is the first detection, and with 2 detectors you see you get a band on the sky. This is like GPS satellites. When you have 2 GPS satellites, okay, and you get a delay, you can only locate your position with respect to the GPS satellites on a ring, because the whole ring has the same delay compared to, you see 2 detectors, 2 GPS satellites, you draw a ring here which is actually symmetric to the line joining the 2 detectors, you get equal amount of delay all over the ring. So by comparing the time delays, you cannot find your position. You need 3. Okay, when you have 3 detectors, then what happens is that, so this is the error circle for the first detection. One more thing, that why this is cut. I am saying that with 2 detectors we can get a ring on the sky, but here it is not really a ring. It is like somewhat cut somewhere. That is because our detectors cannot see all the directions equally. So that disadvantage come to somewhat a bit of an advantage, that we can localize it little better, because we know that if the source was here, the detector would not be able to see it. So it must be somewhere where the detector was sensitive. So now here, if the LIGO India detector was operating when the first detection happened, the error circle would become from there to this small. That is that just to guide your eyes. Now these 2 events, GW 170817 and 170814, these 2 detections happen when 3 detectors were operating, even though Virgo actually did not see this source, because it was sensitive to see some parts of the sky. That was good enough to reduce the sky localization error. So basically the point is that we need 3 detectors, and this is to make it more clear that what happened. Somebody asked during GW 170817, this is what exactly happened. Okay, so first Fermi detected first, even though, meaning the detection happened actually later, 2 seconds later, but their results came first. And with the Fermi detectors we get this overlap, so the signal must be somewhere here. Then LIGO detectors will give you a ring on the sky, again little bit cut because of that this thing detector, this sensitivity, and with Virgo then it becomes much smaller. Then it is still not very small, but nevertheless this could be followed up, and people checked that which galaxy showed a change in the luminosity, and that is how the galaxy was located. This is how we got then this was followed up by all these observatories for weeks, and of course all the observatories in the world, and it has to be a worldwide collaboration, because you cannot observe in the night in optical. So many countries contributed to this. Now coming to the point of why then we need LIGO India. The point is that this sky localization accuracy is not enough. Okay, we are looking at about few tens of square degrees, but it has to be much smaller so that we can localize the sources much better. This is the Earth. This is for the North Pole. This is North America. This is India. You see that right now we have 3 detectors. Let's say Hanford, Livingston, and Virgo. Okay, and their distances are shown in milliseconds. 10 milliseconds means 3,000 kilometers. Now, when we put a detector here, you see that the number of baselines. Okay, if you have a talk on GMRT, then you will understand that how these baselines are important for localization. The number of baselines here was 3: HL, HV, LV, and with LIGO India, you get 3 more: HI, LI, VI. So the number of baselines actually doubles, and their distances are much longer. It's like 1.5 times more. A combination of that plus the duty cycle, that is the amount of time 3 detectors are operating together, etc., you get a factor of 5, about factor of 5 improvement in sky localization. So this is the sky localization situation if you have 3 detectors and a 4th detector at the same place as Hanford, compared to this when you take one of the detectors which were initially planned for Hanford to India, and then this is the kind of sky localization accuracy you get. Okay, so this would mean that all those electromagnetic telescopes suppose the sky localization area shrinks by 5 times. That means the electromagnetic telescopes would be able to observe that spot 5 times more, okay, meaning the integration time could be 5 times more. Let's say that they had 1 hour to observe, follow up. All 1 hour, then instead of spending on 20 tiles, it can spend on 4 tiles. So you get 5 times more observation time, which means that you can observe square root of 5 times further away, okay? Which means that the volume coverage increases by 5 to the square root of 5 cube, which is like a factor of 11. Plus, because you have one extra detector which is very sensitive, like the other 2 LIGO detectors, the probability of detection itself increases by a factor of 2, and these probabilities are multiplicative, so you get a factor of 20 improvement when LIGO India comes operating. This becomes very difficult for people to believe that a detector can actually add a factor of 20 improvement, becomes almost unbelievable, but that is what it is, okay. So we have a paper put in the archive, you can go through it and then see that how even people who work on gravitational waves could not believe that. Okay, so where to place the detector? So there was a study which was done a long time ago to find the location of the optimal location of the detector on the Earth, given the 2 LIGO detectors and the Virgo detector. That turned out to be the middle of the Indian Ocean. So there are 2 possible places where you could do it. One is Australia and one is India, and of course India was better, so we chose India. Meaning India has better people, right? So then where you put in India does not really matter astrophysically, because it compared to it's a broad location, so you can put it anywhere. But many sites were surveyed. Even though earthquakes are not such a bad thing for the detector unless it completely destroys the detector. I mean, a small earthquake will pass by and then we will lose data for, let's say, 1 hour or so. But nevertheless, you tend to choose seismically quiet places, and the place in Hingoli, Maharashtra seem to be optimal in various ways, because you have to find a place which is not too close to a city, because then that will have a lot of seismic anthropogenic noise, but it cannot be too far from a city, because then people would not be able to reach there and the detectors cannot be carried to the site. So typically we chose like 50 to 100 kilometers from a not very crowded airport, etc. So all these criteria put together, this seemed to be a good place. Then IUCAA is one of the lead institutes which is executing this project. Other 3 are 3 Department of Atomic Energy Institutes, RRCAT, DCACM and IPR. What I wanted to tell you is that one of the task of IUCAA is to do science build-up, and then there are a lot of exercises that are done to tell people that how they can contribute to LIGO India, etc. So these are some pictures of the LIGO detectors, just to give you some idea about the scale. Yeah, I think I'll stop in the next 5 minutes. So this is typically the schematic of a detector. You see, these are all chambers where beam splitters, the mirrors are placed, and this is like 4 kilometers. It's 1.2 meter diameter, and you can see. So this is keeping me. So you see that people are standing here, and then these are the actual scale of the detector. It is on the 4 kilometer diagram, it looks small, but actually they are very big equipments. And these are the mirrors and the suspensions of these things. I mean, each one of them had tens of PhDs. So, and still on. Okay, these are the optics and all those things. Now, I did not have much time to talk about data analysis, but I just want to tell you that why the waveform modeling was essential. You see that if you have some noisy data and you have a signal whose shape you know, but you don't know where it is, then what you could do is that you place the signal somewhere, take a correlation with the data, and so on, and keep plotting the correlation. You will see that where the signal matches this model signal called template matches the actual signal, you get a peak. So this is how this involves a lot of mathematical techniques to do it, and also this is not just one single waveform. There are almost 1 million waveforms which you have to look for, which increases the chances of some part of the noise mimicking at least one of them, so increasing the false alarm rate. Okay, so I will skip all of these signs potentials now, and I just want to focus on this and end. Okay, maybe this and the next one. That's all. You see that this is the thing I was talking about. We are at the center. Okay, these yellow dots represent binary neutron star mergers. These white dots represent binary black hole mergers. Okay, and these circles are at different sensitivities. This is third observing run sensitivity. We are at the fourth run right now, observing run. This A plus sensitivity is where LIGO India is supposed to start operating. This Voyager, this orange one, is the sensitivity that can be achieved with a 4 kilometer detector in a different configuration. Now you see that, and this is redshift, radially outwards is redshift. You see that the binary, so if we reach when LIGO India starts operating, almost like half the binary, more than half the binary black hole mergers will be observed by LIGO. See, all these will be observed by the ground based detectors. What will not be observed are these, the neutron star mergers. So initially people thought that this is A plus right here, that all these objects are present here. Okay, maybe there also, but certainly here. But that is not the case, we know now, because the number of detections here is only 2% of this. So people now understand that these are these things are at a more distant part. But the subtlety, what I was saying is that it is not that the number of binary neutron star mergers is less than this, but just that we can detect them only when they are close enough at the current sensitivity. But in this vicinity they are not there. So you have to get to the next generation detector, the Cosmic Explorer and Einstein telescope, to detect all these, okay, which are being done. So this is what I was saying, that next thing is that, so there is a, so Einstein telescope is in Europe, meaning being built in Europe. It could be an underground detector with this kind of arm length, may not be. It is most likely going to be a 10 kilometer detector, and there is a Cosmic Explorer idea, which is for the US, which can have 40 kilometers arm length. Okay. Now, of course, this is going to be the future. Now, the thing is that many times people say that, well, lot of the components of the LIGO detectors are going to come from LIGO US, LIGO India detector, because as I said that there was a plan for building 2 detectors at LIGO Hanford. So those components are going to come. And people wonder like why we are not building all these components. Okay, actually a lot of the components have to be built because they are very old. But the main point is not that. We are going to use the same technology as LIGO, okay, to start with, so that we can reach more or less similar sensitivity. And there the problem, many times people ask like, oh, why are you using the same technology? Why don't we go for the better technology? Well, that is what was tried out in, for example, in Japan and Italy in Virgo detector. There is a bit of uncertainty whether it is going to work or not. But the point is that once we start operating with a detector, LIGO India detector, LIGO India being the youngest detector, it has higher survival rate than the LIGO US detectors, right? I mean, LIGO US detectors are 30 years old, so the vacuum at some point may fail and so on, but the LIGO India detector is going to continue. At that point, for this next generation detectors, we can create all the technologies, whatever people are excited about, to develop at LIGO India, because that time there will be a role reversal. Right now we are using the technologies of the established detectors in the US to build LIGO India, but we can develop the technologies needed for the next generation detectors, which will be built in Europe and America in India. So there is no problem. For all those creative minds, there is enough material available. So now but the first task is to build LIGO India on time, and hopefully we believe that will happen in by 2030. One thing to note is that when government funds such a project, so LIGO India is going to be a multidisciplinary mega science project on Indian soil. Not many such projects are there. When such a thing happens, the reason is not just astronomy, but it connects to various technological developments. Okay, so in fact, I was telling somebody that you name any concept in physics or in engineering, okay, there is a very good chance that it has an application to LIGO India. Okay, it could be computer engineering, mechanical engineering, like and in physics, like for example, like you say condensed matter, astrophysics, numerical relativity, whatever, quantum mechanics, classical mechanics, everything has an application. So this is why these projects are beautiful, because then it provides a platform for exchange of expertise. Okay, I am not going to talk about the space-based detectors, unfortunately, except for one thing, that these are the present space-based detectors which are probably going to fly in 2035. This is the LISA detector, and these are the ground-based detectors. There is a gap here, and we are hoping that India will put a detector there in the decihertz band. Okay, so I will stop here. So this is the present situation. We have made some transient detectors in the 100 hertz band, let's say here, milliseconds. The whole frequency band has many sources, many different probes. Hopefully in the next few decades all this will be achieved. Okay, I will stop here now. I think you are hungry enough that you are not going to ask any questions. That is the best part. Okay. Yeah.
LIGO can detect white
White-hole merger. So first of all, the white holes have to exist. I don't know if they exist. I actually love them in movies, but I don't know whether they exist in practice, and even if they exist, what exactly they are going to do. Okay. For black holes are like, much more low profile objects. They're essentially stars, but they have collapsed so much that the light cannot come. So they will go around. White holes, I don't know.
See, white holes have been proved to be unstable. Even if white holes emerge, they soon collapse to a black hole. More interesting question, which long time by the Goa conference, Sanjit and I discussed, is that even if you have suddenly a white hole creation, but it's unstable, it will collapse to form a black hole. One should calculate what kind of...
The gravitational wave will be emitted there, and maybe it will create a gravitational wave background, because such creation destruction can happen continuously in the early universe. But then you need some quantum effect to ignite it, right? I mean, it cannot happen because you need statistical fluctuations triggering those. So I don't know how otherwise you will trigger them.
So, of course, the old theory would say that whenever a black hole formed, the singular matter appeared as a white hole.
That is this.
The old
This wormhole.
Rosenfeld diagram.
That will.
That was classical, without invoking quantum. I'll tell you something.
Yeah.
To sort of have a better sensitivity at very low frequency, can't one use adaptive seismology? The adaptive optics people, they correct for seeing what kind of seismic oscillation is happening. We can correct at the point of suspension of the mirrors.
Right. So the thing is that I did not discuss this part. So at lower frequencies, not just seismic noise is there, but also the Newtonian noise will come into the picture, which is of seismic origin. Okay. So what is going to happen is that the ground is fluctuating. This is going to the Newtonian gravity will be coupled to the mirror. That is going to create a noise. This noise cannot be shielded. Okay. Because it is gravity. It is like mass fluctuation. So what do you do to deal with this is exactly what you are saying. So what happens here is that it is not yet there in the detectors, but it is assumed for all the next generation detectors, it is assumed that Newtonian noise will be reduced by a factor of 10. Okay, nobody has shown it yet. In principle, there are some papers. My student also worked on that. I am an author here. The idea is that you place a set of seismometers across the detectors, but you don't know the actual coupling from the seismometer to this. There is no transfer function is not known. But what is used is an adaptive noise cancellation, that you have the signal and then you are subtracting out a linear combination of all the measurements which were done using these seismometers. Now, because you don't know the transfer function or the coupling matrix, what are you going to subtract? So the idea is that if you have any data set and you are subtracting out a noise n, okay, let's say that forget about data set. Let's say you have noise n1 and you are subtracting out n2, where hoping that n2 is part of n1 is a correlated part of n2. The only time the variance will go down is when n2 indeed is correlated with part of n1. Every other time the variance is only going to increase because the minus sign does not mean anything. So what this method does is to reduce that variance. That now you start changing the coefficients of that matrix in such a way that you finally start observing a reduction in the variance, which would mean that you have actually subtracted out the correlated part of the seismic noise. But even with this, you cannot go beyond like couple of hertz. This is assumed already. In this plot, you see this part here, it is assumed that you are subtracting out that. Otherwise, you would not be even able to go there. Like this is 10 hertz. We are right now here. So this assumes that such a subtraction.
There are 4 mirrors there.
Yeah.
Where at least the fabric curve, you need 4 mirrors.
Yeah.
But why not have the seismometers near the point of suspension of each mirror, so that you locally sample what is happening?
Yeah, that is there because you see it is this is here is one these are here also.
There is also a beam splitter. There also one needs a.
Yeah, so this is so these are these locations. So there was a seismic model based on that, but you have a finite amount of money to buy seismometers. So here it was assumed that you can buy 20 and it is not just normal seismometer, it has to be certain good quality. So let's say you can buy 20 seismometers. So where are the optimal locations to place those seismometers was basically what my student did. So that these are the locations.
So from gravitational wave signal, can we say anything about the spin or charge of the black holes?
Charge one would be like it is possible, but the thing is that it will be degenerate, probably will be degenerate with the mass. Okay.
Or with the angular momentum, because Rational also x square minus q square.
Yeah.
So q is also like the angular momentum.
Like the angular momentum. So it will be difficult to degenerate.
There has been a study in the ring down profile where you find out, like you look for a Kerr-Newman solution, and the Cambridge group did come out. Initially, that was anywhere difficult. The Cambridge group did come out with a solution, and there is a group in our collaboration who tried to constrain the charge. The only problem is we don't have enough ring down data to get a good enough a converged posterior, but it was consistent to 0.
I will believe them. I mean, I think, like,
It's a method. That's all that
I know. I think these things will become very reliable in 1,000 years or so. I think right now the problem is that the primary modes, mass and angular momentum, it will probably take 20-30 years to get there. The ring down mode.
It depends on what sources you're looking at.
Of course, LIGO India can do it. Maybe we'll see. The thing is that so basically the point is that if the ring down modes will be a function of 3 parameters as opposed to 2 parameters. First, let us assume that there are 2 parameters and try to prove that that is the case, which right now will take probably, like with LIGO India there is a chance, but probably with the next generation detectors, like in 2040s, something probably can happen with the using ring down for no-hair theorem test.